Morning. So it's a great pleasure to welcome you all to this week celebrating the 60th birthday of our friend and colleague Frank Loray. And there will be an opening, more formal opening ceremony at the end of this day. So I will not take time from Laura, who will give the first talk on the underlying geometry behind the analytic invariance of singular foliations by curve on the plane.
Thank you very much. And thank you very much for the organizers for inviting me to be here. It is a pleasure and an honor for me. In fact, to be here celebrating Frank is an enormous, enormous pleasure. He, as all you know, is not only a great mathematician, but a really great, great friend. He takes care of everything, of his family, of his students, of his friends and colleagues. And well, un abrazo muy fuerte. Now, the aim of the talk today is to give some objects that give us some geometrical explanation of invariants that were previously obtained for dicritical and non-dicritical foliations. In order to talk about analytic invariants, it's good to recall the definition that we will all the times use, and it is for analytic vector fields. If we have C prime equals to V sit, sit and C prime equal to W sit, we will say that they are analytically equivalent if one can find an holomorphic transformation with inverse such that for each solution at a given point, H takes this solution to the corresponding solution of the other equation. So this will be phi W of T HP. So if we take care about the parametrization, so this can be written briefly like this. If one takes care about the parametrization, we're talking about solutions of differential equations. But if we are not taking care about the parametrization, then we are taking leaves to leaves, and we're talking about foliations. So in that case, we will say that it is analytically orbitally equivalent foliations. And moreover, if one asks for the derivative of H to be the identity map, then we are talking about analytically, orbitally strict equivalence. So I will use strict equivalence. I will use that this kind of equivalence. Now, there are some classic results that give us the linearization of vector fields, and we know the conditions given by Poincaré, the theorem of linearization of Poincaré, and the conditions given by Siegel and Bruno. And all these theorems give us a way to go to make analytic equivalence of the vector fields with its linear part. But at this moment, we are not going to talk about vector fields that have linear part. We are going to look to vector fields that doesn't have linear part. So what we are going to look at is for vector fields that are written these are homogeneous terms. Polynomial homogeneous. And here we will have the other term. Plus higher order terms. They are analytic. Let me name this like V, it's Y. Its principal part for me will be Vn, will be defined as Pn Qn. And this is in the complex setting, and N will be greater or equal to 2. Now, in this case, one doesn't have linear part, so the usual is to look to the blowing up transformations. So I will take the coordinates xu as usual, where u is equal to y over x if x is different from 0, and the other chart given by Vy, where V is y over x, x over y different from 0. So by performing this kind of transformations, we will get an equivalent equation. I will write it like this. That is given like x p tilde un u xu over r n plus 1 1u plus x and higher order terms. For this equation, one gets the first division among this equation, and it is given by the cases r n plus 1 is non-identically 0, and the other case r n plus 1 identically 0. This case is called the non-dicritical, dicritical, and this is the dicritical case. So I will start with the non-dicritical case, and so for, see?
Can you define R and
Oh, thank you. R n plus 1 is, thank you, x qn xy minus y pn xy. So this is in coordinates xy. And when you pass to these charts, then you will have here a polynomial in U that for this non-decritical case, I will write it like this, R n plus 1, 1U. We will assume that we have n plus 1 factors, different points. We have p n plus 1 pairwise different points, roots of this polynomial. And as you can see from this equation has x equals 0 as invariant line. And at the points p1, pn plus 1, we have, at all these points, we have roots here of the polynomial, and therefore we will have singular points of the vector field. So what we will have is something like this. We'll have an invariant sphere with marked singular points. And so on. We have these singular points, and the sphere is invariant, and the neighborhood of the C2, a neighborhood of the origin in C2 will give us a neighborhood of this sphere. So we will consider at a non-singular point a transversal, a local transversal to this line, invariant line, and we will take the fundamental group. That is to say, we will take loops, gamma I, and so on. All these loops, and for each loop, we will take for the solutions that are near to this invariant line, we can take a well-defined transformation from gamma to gamma, is the holonomy map, and what we need to do is to lift this loop to the solution of the equation. So here we'll have some transformation. Here we, as the points are simple, we will have here some separatrices, and we will assume in the genericity conditions that they will be linearizable singularities. So we get a map delta I of theta, if theta is the parameter of gamma, that will be given as e2 pi I lambda I hat theta plus higher order terms, where lambda I, this exponent, is Camacho-Sad's index. So it happens that when we take the sum, it is equal to -1. And this is because we made a single blow-up. And the composition of these transformations, delta 1, delta 2, delta n plus 1 is equal to the identity map, because we are in the sphere, and this is property that it has. Now, many years ago, in the 70s, René Thom asked about the analytic invariants of this kind of foliations. The projection can be seen in this way. Well, we have here the separatrices, and he asked about the analytic invariants of this kind of foliations, and he itself conjectured that the invariants were the separatrices, the set of separatrices, together with the holonomy maps in this statement, in these coordinates. Some years later, Robert Moussu gave a counter example to this conjecture, and he itself made a conjecture that some years later was disproved by Mattei and Javier Gomez Montt, giving the deformation moduli for this kind of equations. And some years later, in in 2012, together with Ernesto Rosales, Sergei Voronin, we were able to get the analytic invariants for this kind of equations. So here, if we take all this kind of transformation, one can define a group, and it's generated by all this transformation, G1, delta, sorry, delta, delta, delta n plus 1. And this is the monodromy group. And what we got is that two differential equations in the neighborhood of the singular point, the origin in this case, are analytically, orbitally strict equivalent if and only if some invariants tau b Cij, the group of holonomy, the analytic class of the group of holonomy coincide with both. If this is the definition, then if we get that this is as well tau w. Where does these constants, these are constants, these are in C2, in C, sorry, and where does this constant come from? We got a formal normal form that has the principal part that I stated here. Then it has a Hamiltonian part with finite number of terms and a radial part. So the coefficients defining this Hamiltonian part give this kind of numbers that we are taking here. So at that time, we also gave a realization theorem, given this information, the information of some constants, the proper number of constants, and let me put it like here. Alpha is the number of theCij's that we are getting, and given the constants, and given a conformal group of a group of conformal transformations having these two properties, then and something important, the group needs to be a non-solvable group. We get here also other genericity assumptions given by some determinants that need not to be 0. And in such case, one can not only get the invariants, but realize these invariants. Now, this is for this case, and for the... See? Strict, yes, is that here you have the derivative of H is the identity map. Is to work with less parameters, that's all. So the other case is the critical case. And for the critical case, with the same authors, but in 2005, we got the R, let me put like this, RM, the same R, but I will put M, is better to use it like this. No, it is not better. RM plus 1. Yes. We got some equivalent classification that is given like this. We will have
Rn plus 1 is equal to 0 now.
Is
right?
equal. Oh, thank you. The critical case. Thank you. So in this case, we will have our sphere. You can see here that this term is equal to 0, then you can reduce the equation, and the invariant line that we had in the first case is no longer invariant. We will have that the solutions are transverse to the sphere, and that we will have some unavoidable tangencies where the solutions are not transverse to the sphere. So we will have this kind of behavior, and we have some points Q, J, where the things are no longer transversal here. So we have these points of tangency, and with these points, a natural involution in the sphere appears, and if you have U, here you will have I U star will be I J of U. That is an evolution around the tangency point. So in this case, what is important to get is that one will have some tangency points. I will mark them Q1, Qm, that are the points where one doesn't have these transverse solutions. And together with them, we will have some involutions. These involutions, together with these points of tangency, are let us give a formal normal form again that is given by the following. I won't put the formal normal form, it's long, but I will take again, as I did there, the invariants that are given by some constants, different constants, and the set of involutions. Something to say here is that here, when we project, we will have at the x, y coordinates, we will have, let me put it like this. Something like this. Here we have y equals to ux. Here we will have tangency y equals to u star x. And here we will have the tangency that is collapsed, y equals qj x. This corresponds to this point. So, and a lot of curves there that are collapsed. Now, for this, one also has this Thom's invariance. Again, the theorem says two vector fields are analytically, orbitally, strictly equivalent if and only if their Thom's invariant coincides. Their Thom's invariant coincide. Now,
Laura,
sí.
so you're assuming that the tangency are simple.
Simple tangency under genericity assumptions, yes.
There are no singularities.
No singularities among, for this you need to take, as you don't have these terms, you have the zeros of this part and the zeros of these other terms, the first one that is non-zero for x equals 0, and you can take away from singular points. So the tangencies, thank you, the genericity assumptions are that these points of tangency are simple tangencies. Now, and the roots are pairwise different. This, not the root, the tangency points are pairwise different ones. Now, when we work with this case, and before that, when Sergei Boron worked with this case, he proved a rigidity theorem. Formal implies analytical, and we use it here, this theorem, and we use as well the non-solvability of the group that is needed to make a relation among the monodromy groups. So we need to use this kind of theorems, but when Sergei proved this theorem, he was needed to make an auxiliary foliation. In his constructions, he used an auxiliary foliation that was dicritical, and he was needed to take these separatrices to be part of these curves, and this condition give him some conditions on the foliation that is auxiliary, and he got some dicritical foliation, auxiliary dicritical foliation with tangencies. And when we worked with this kind of equations, we were needed to use a non-dicritical foliation. And this gave us the idea to, we wanted to have some geometrical explanation of these constants. And we didn't succeed for a long time. And we then began to think not about one foliation and its constant, but foliation pairs. Dicritical and non-dicritical foliations put it together in order to get some light on these constants. So I am going to talk about this. Let me, whoa. Well, I will put it here. For this kind of equation, non-dicritical, we will take a local model. This local model is going to be defined in the XU coordinates, and it will be given by x point equal to lambda I hat x, and u point equal to u minus PA, no, S x u, no, u minus PA, sorry. Now, we will take as well another foliation that will be defined like this. And these curves are given by u equal to Si x plus pi. This Si at 0 is equal to 0. And it will have no singularities at its transverse to this other foliation. So we will do the same here, but let me fix some ideas first. Here we will have an holonomy defined, and we are looking to get some information. We want to give some P1, Pm plus 1 collection of points, and we would like to give some G, a group of conformal transformations. assuming that this conformal transformation have this pi lambda I, hat. And assuming that their composition is the identity, and assuming that the sum is n plus 1. So there is a theorem by Alcides Neto in '87 where he realized this kind of information, and in our case, it will imply that there exists a foliation f mu that has these points as singular points. Around these points, we have defined the holonomy that is given by this information, and all this along the sphere repeats, and one has a non-dicritical foliation, and so on. Now, this is pi with the holonomy. Now, together with this foliation that Alcides constructed, realized, this foliation has straight lines as separatrices, one can construct a foliation that is given by straight lines. So what we are going to do is to glue this local model. To do this, one needs to make a transformation Ci that gives this foliation to itself, but that takes this yellow foliation to straight lines. This can be done in an holomorphic way, but for the singularity. So this model that comes from here will be pasted in here. We will have this gluing, and we will have here the gluing of the foliation. One needs to think about an annulus. It's an annulus. Whoop, here. Whoop. Okay, so one pastes this model, and for the non-dicritical setting, what we will have, I'm sorry, I need to erase somewhere. We will have some models that go like this. Let's say that this is Qj, and we will have here some we have the involutions, and we will have here defined some function gu that is given by u minus qj minus the involution iju. And we will have as well here a parameter that depends only on x. So with this information, we can also make a straight foliation in order to glue it there, in order to glue it in that construction. And we will have these curves. Again, from here to here, we have problems with the singular points to be holomorphic. Everything is holomorphic, but in the singular points, but we will be able to extend there as the identity map, so no problem will be there. So we will construct, here our qj, and our foliation here will be extended like this. So we will glue this model here. Now, what it was very beautiful from the Alcides theorem is that the information that one has in the singular points are the Camacho-Sad index, and we assume them to be equal to -1. So this means, and we have a normal here foliation, and this gives us the chance to talk about Grauer's theorem. So one can use Grauer's theorem and it will give us a biolomorphism between our foliation that was constructed by pieces to a foliation that is given by the blowing up of a singular point. So this foliation has now the separatrices are not straight lines, but what is interesting, what I want to state here is that we will have these singularities, and we will have the other foliation that will come like this. Here again. And these pair of foliations will mark some tangencies. Both foliations are tangent one to each other in some curves. Oops. And for the critical case is the same. We will have here some foliations. Wait, I lost my, okay. So we have these tangencies, and these tangencies, this collection of tangencies give us the following. Whoa, here. We have a collection of tangencies, tangency curves, Pi, Qj, I going to from M, and I equal to n plus 1, and j going to 1 to m. And these tangencies curves will be crucial to understand these invariants. First of all, one can, as I showed, one can make a realization theorem for this information, and as well for two foliation pairs with the holonomy mark and the involutions mark, one can give local models, and two pair of foliations are analytically equivalent if and only if they have the same local models. So all this can be proved, but what I want to look at is that these tangency curves give us some transformation from the local models to the foliation that is holomorphic, and in the other, for the critical cases as well. And if here from our local model to here, it will give us some transformation that one needs to clean. The parameters of this transformation, one needs to clean it in order to have a good parametrization of the tangencies curves. This is not a simple task, but one can give the parametrization of the tangency curves, and for the case m equals to in n minus 2, you will have that the analytic invariants of these curves, they are finitely determined, analytically determined, and the analytic invariance of this set of curves of tangency for m equals to n minus 2 is equal to the sum of these invariants and these other invariants, beta. So the fact is that the sum of these invariants will give, will be in correspondence with the analytic invariance of the tangency curves for this pairing non-dicritical and dicritical. And this gave us the needed geometric interpretation. And when one thinks about it, is what was more or less natural. These are the places when one loses the coordinate system. These places of tangencies are the places where one does not have coordinate systems. So, well, this is what I wanted to talk about. Thank you.